So yes, good afternoon and welcome again. This is a special slot for the communication and signal processing seminar. We normally are on Thursdays, 4 to 5, but we had to cancel Alex's talk earlier in the semester, so this was a good time to have this. So Alex, so yes, before I get started, I should thank Shelley Feldkamp as always for helping make the seminar series happen. She's the heart and soul behind this whole operation, and nothing will work if she doesn't do what she does. And I should also thank KLA and the two research groups, NCIS and SIPML, for the support in running this seminar. So yes, I'm delighted that we could finally get Alex Dimakis to come and give a talk. I would like him to come and visit in person sometime, but that'll happen at a different time. He's already doing enough for Michigan, so we may as well bring him here in person. So he's currently a professor in the EC department at the University of Texas at Austin. Before that, he spent a few years at USC. And well, a little before that, he got his Ph.D. from UC Berkeley. And well, before that, he got his diploma degree from National Technical University of Athens. Now, his research interests are quite broad. His initial work was sort of on information theory and coding, which he still retains some interest from what I know, including index coding, and he has looked at things in caching. But he's been moving a lot more into machine learning, and looking at GANs, looking at neural networks, trying to understand that. And so today's talk is on deep generative models and US problems. He's taken the deep dive, so let's see what he says.
Great. Thank you very much for the invitation. So I will be talking about deep generative models and inverse problems. And most importantly, this is joint work with many of my students, postdocs, collaborators, including Eric, who's a professor in UT Austin, and Augustus, who is at Google Brain. So to start, and I would love to have an interactive conversation and questions. If anybody wants to write on the chat or interrupt me, I love that. It makes it much more fun for me also. So the central problem we have is, how do we model high dimensional distributions? This is, of course, not a new thing. This is a super classic problem that many people have studied for a while. So we want to represent high dimensional signals. And when I say high dimensional signals, I want you to think of natural images, audio or time series or wireless channels, for those of us who are also interested in communications, or MRI scans, which are like images, or they can be like video, and so on. So just to explain the problem in a very simple setting, let's start with a very low dimensional and binary case, which is have two random variables, and they're binary. Okay, so they take the value 0 and 1. And we start with data. Okay, so we have two variables, x1 and x2. And we see that in the first sample, x1 got the value 0 and x2 got the value 1, and so on. And we have a bunch of samples that are drawn independently. Let's say that's the only assumption. These variables are not independent with each other, but they're IID from a distribution. And the first central problem we have to face is learning this distribution, or we can call this fitting a model. So of course, as we know, a very obvious way to solve this simple problem is to create a histogram where we're literally counting what fraction of time did 0, 0 appear, right? So if I had 100 samples, I'm going to count, 15 of them were 0, 0. So I'm going to estimate the empirical frequencies here. And these numbers is an estimation of the joint distribution of these two dependent random variables. And they hopefully sum up to 1 or greater or equal to 0. And we can easily solve this learning or fitting problem from data in this very simple case where we have two binary variables. Now, if after we have learned a representation of the distribution and we have fitted to data, we can do a few other things. One of them is this interesting problem that's called sampling, where I would like to produce some new tuples, let's call them. Like, for example, maybe I sample 0, 1, and maybe now I sample 1, 1. And I would like some machine that spits out samples that have the same statistics as the real data. And actually, I'm going to do this by just sampling from this. And if you think it's a nice little puzzle in probability, how you can sample from this distribution, you can make a unit interval where the lengths are 0.15 and so on. I assume and hope you can see what I'm writing with my hand, right? Yes? No?
Yes, we can.
Yes.
Thank you, great. So you can make an interval, split it into lengths proportional to these, and then just sample a uniform random variable in 0, 1, and you will be sampling, let's say, from this distribution and so on. So sampling sounds like extremely useless to do, but it actually has a lot of applications. Like, for example, in a privacy setting, you may generate artificial data that have the same statistics as the real data without releasing the real data, for example. Now, there are many other things you may want to do once you have this, once you have learned this distribution of the data, like conditional sampling. For example, let's say that you observe x1 is 1. What is the distribution for x2? Or can you sample from x2, condition that x1 is 1? You can also think about denoising. Maybe you see a noisy version of x1, x2. You want to do, let's say, maximum likelihood denoising. Or you can ask, what is the likelihood of a specific tuple? How likely is it to observe 1, 1? And this is useful, for example, in finding outliers or checking if the distribution has changed in the middle of the process, and various other tasks that are in general called inference tasks. So everything here is super simple when you have two binary random variables, but it already becomes quite interesting when you have, let's say, 100 binary random variables. Now you have 100, every tuple is 100 bits. And now if you try to represent the joint distribution for 100 bits, that's a 2 by 2 by 2 by 2 100 times. So it's 2 to the n joint distribution with n being the number of variables. So you have absolutely no hope of doing this non-parametrically, as we say, which means you have to make some other assumptions about this distribution. Otherwise, it's hopeless to even store this thing. Even if somebody gave this to you, you wouldn't be able to even store it anywhere, right? Because 2 to the 100 is a pretty gigantic number. But what we actually will do in this talk, and what I'm actually interested in, is even worse, because instead of having 100 variables, we actually have images. And the images I will be showing you are 1,000 or 1,024 by 1,024 pixels. And they also have 3 colors. So it's actually 1,000 by 1,000 by 3. So it's 3 million dimensions. And every pixel, every color channel is not just binary. It's actually a continuous number that's modeled with 8 or 16 bits of accuracy. So the dimension of this, if this is a sample, of course you know who this is, but I don't know if anybody knows who this is. Does anybody have a guess? Or do you know who he is? Maybe you don't. Anyway, we'll see him later. Okay, he's a cool guy. So. So we have images of people, and we want to learn a distribution over faces of humans. And not only do we want to learn this distribution, we want to do things like this. We want to do sampling, where we can produce fictional images. And we want to do conditional sampling, where maybe I observe half a face. I want to sample the bottom half. I want to do denoising, where maybe I observe a noisy image, or many other things, finding outliers, finding distribution shifts, and so on and so forth. So the centerpiece is how are we going to represent the distribution on many variables in a way that is succinct, so it can be done efficiently and can be at least can be represented in our computer, but we can also perform inference tasks on it. So there has been a few ideas. Classically, this is a well-studied problem, and there have been many ideas, of course, historically. The standard one is to fit a multivariate Gaussian, of course, which will model pairwise interactions, but nothing more than that. So it's not going to be a very descriptive model. Then people have used conditional independence, which has been a centerpiece for all this theory for graphical models and Markov chains and so on, and which is a beautiful theory and also has found a lot of applications. And then another family of results has used sparsity. They say that this image or this high dimensional signal may be very high dimensional, but it has simple structure. And that structure is by being sparse in a known basis or even in a learned basis. So these have been the things that have been studied intensely for more than 15 years or so, maybe 20. And I just quickly want to say that graphical models and Markov chains that use conditional independence have been a great success. They're actually used in channel coding, like LDPC codes and other types of error correcting codes are using graphical models as their representation and inference mechanism. And this has transformed all of communications. And similarly, sparsity, which is a way to represent images, video, audio, and so on, has tremendously impacted the world by all the compression standards that we're all using all the time, and also, for example, in improving MRI and other imaging methods using sparsity-based techniques. So these are all very successful methods, but this is not what this talk is about. This talk is about another idea, which is idea number 4, I call it, where I'm going to basically not use any of those models. I'm going to use deep generative models instead. And I want to first tell you what that means, and then I want to show you how we can use them, because the methods, the algorithms are going to be different from the algorithms used for graphical models and from the algorithms used on sparsity. The central idea of a deep generative model is it transforms simple randomness, like independent, normal random variables, using a neural network to produce complicated randomness. So from simple randomness to complex randomness, the simple randomness is low dimensional, typically, whereas the generated signals are high dimensional, like images. And deep generative models have many flavors. You may have heard of variational autoencoders, or generative adversarial networks, GANs, or even untrained generators like deep image prior or the deep decoder. I saw that Madi gave a talk last week, so he spoke about this, which is great. I won't be talking much about untrained models in this talk, but they're also a very exciting type of technique. And then there's other methods called invertible flows that actually do not have a low dimensional Z, but I won't talk about them much today, but they're very interesting. So when I talk about generators in general, I want you to think of the following thing. It's a feed-forward neural network, which takes random noise, like 100 independent Gaussians, let's say, that's going to sit here, multiplies by a matrix, has a ReLU activation and nonlinearity here, produces a vector, multiplies by a matrix, has a ReLU activation, produces a vector, and keeps going like that. And then at the end, it produces a bunch of numbers that I can stack in a 2-dimensional array, or a 3-dimensional array, like this one is 64 by 64 by 3, because there's 3 channels. And I can somehow train these weights of this neural network so that when I feed random noise here, these numbers start looking like natural images. And that's pretty amazing. And this is done by a generative adversarial network. I'm not going to talk about how these are trained, and I don't really care about how they're trained. As long as somebody gives me these matrices, I'm going to use this as a black box. So this is how it's trained in practice. I'm just showing you an example. And you can see that as it is being trained, it starts producing realistically looking images. And I want to emphasize again that these are not real people. These are just dreams of this generator. When I feed in random noise, this is called the latent code, or the input vector. I feed in a random input vector. I get some pixel values that look like a human, but this is not actually a real person. So a deep generative model mathematically for this conversation is going to be a function that takes k dimensional vector that we call z, and produces an n-dimensional vector that we call g of z, and has 2 properties. It's differentiable almost everywhere. So it's basically differentiable except at the points where the ReLU activation has a non-differentiability, but that's a measure 0 set, and it actually is ignored when we do gradient descent. Otherwise, you can break ties arbitrarily with a subdifferential if you want. And then the only other thing you need to care about, okay, first of all, it's also obviously continuous because it's matrix multiplication and ReLUs. And it's also learned from samples using sophisticated algorithms like variational autoencoders and GANs. But you don't have to know how it's learned to use it in this talk. Any questions?
So Alex, I have a question. It's more philosophical. And so there is some sense you're saying that these images or whatever this data you're looking at, these are distributions that can be expressed or closely not expressed, maybe approximated using this low dimensional noise.
Yeah. So we can think of this generator. We can think of it as a machine that takes a specific vector z and spits out a specific image. Or we can think of the whole distribution that is created by when I feed into this machine the Gaussian independent measure, and I get some complex distribution in Rn. Now, indeed, this complex distribution will lie in k dimensions. There's a nice result on that. If you have a map that's continuous in Lipschitz, the Hausdorff dimension of the output is going to be at most k. So indeed, this manifold that is created by this generator lies in k dimensions, but it is, of course, in the ambient space of n dimensions. And we are arguing that it can actually capture all of real faces or real dogs or real bedrooms or other types of images that we have trained generators for. Is that making sense?
Yeah.
Yeah, and we will see if that's the case. So another thing we can do is we can pick our favorite vector, like 1, 0, 0, 0. This is a 100-dimensional vector, and another 100-dimensional vector, like 1, 2, 3, up to 100, and do linear interpolation in the latent space and pass every vector through the generator, and we're going to see images. And we would like to see if the images are just jumping in a discrete way from one face to another, which means this generator has just simply memorized maybe 100 images and just showing one of them to us, or if it smoothly interpolates as it travels on the manifold of generated images in the dimension of 13,000. This is 64 by 64 by 3. So I'll show you a demo that we got that shows the interpolation. And you can see that it smoothly translates from one face to the other. So all the things that are being produced by this generator indeed look like human faces. These are experiments using DC GAN, which is a low-dimensional 64-dimensional generator, but later we'll use more modern generators. Now, so everybody has been using these generators to sample images. So there's this New York Times article that Clayton posted on the chat, and many others like thispersondoesnotexist.com, which will create fake images that look real, like these ones here. And now they can do it in high resolution too. So this is kind of cute and used to create fake profiles on Twitter accounts and stuff like that, as this New York Times article explains. But I wasn't too excited about that. I said, this is cute. Actually, it's remarkable that it can do it, but it's not useful, right? So the main message that I have in this talk is, okay, these modern generators produce amazing pictures. They look like real humans. But what can I do with them other than make fake profiles on Twitter to make bots and so on? And the answer to the central message of this talk that I would like you to take with you is, if you have a generator for a class of images like faces or even wireless channels or anything else, and you have built a machine that can generate it, you can solve a ton of inverse problems using that machine, including denoising, inpainting, compression, compressed sensing, outlier detection, source separation, MRI reconstruction from, let's say, Fourier projections, phase retrieval, and all kinds of problems. Basically, once you understand this concept, I argue that it cannot be unseen. That you go from thinking of a generator from being a useless but cute thing that makes fake faces to something that's extremely useful for a million problems that anyone can think of. Okay, so that's the central message of this talk. Now, this is the outline, and I'm realizing I'm already 18 minutes in. So I'm going to first talk about the first paper that we wrote on this problem that's called Compressed Sensing Using Generative Models by Bora et al., ICML 17. And there are two parts of this paper. There's an algorithm that I'm going to show you. And then there is some theorem that says, that gives some sample complexity bounds if the matrix, the measurement matrix in the linear inverse problem satisfies something that's a generalization of RIP, if you are familiar with compressed sensing theory. So we basically generalized the compressed sensing theory, which was using sparsity, to the case of signals created by a generator, a deep generator. Then the second part, which is smaller, I want to briefly talk about the emerging theory of inverting deep generative models. Inversion is just the most basic inverse problem where you observe a full image and you want to reconstruct it. So I'll mention some papers briefly on this. And then finally, I want to tell you about a very recent paper that we have that is going to appear in this deep inverse workshop in NeurIPS, I guess in 2 weeks or maybe in a week and a half, And then we have two extra algorithmic innovations, what we call intermediate layer optimization, and also using perceptual distances in addition to mean squared error. And the results that I'm going to show you right now are basically using this latest technology. And they can be very, very good in high resolution. So yesterday night, when I was working on this talk, I took Vijay's picture from his webpage, which is unfortunately quite low resolution. And I wanted to solve an inverse problem using our latest algorithm. So we remove these pixels. So the problem is now you see this image, you know that these pixels are missing. Okay, so when I color this here, we know we code these as missing pixels. And we have an inpainting problem. We're trying to make the generator dream of an image that not only looks good, in the sense looks realistic, but also agrees with the measurements, which is agrees with the observation, which are all these pixels here, but not, of course, the pixels that are missing. So my student yesterday sent me this image, and I'm like, okay, yeah, sure, that looks pretty good, but it doesn't really match Vijay, and also it looks more like a white guy. So we changed the intermediate layer optimization parameters, and we got to this, which is kind of an interesting twist. And then after, with more tuning, we got to this reconstruction. So this final reconstruction is using intermediate layer optimization, and we use, of course, a very powerful GAN that's called StyleGAN2 to solve this problem. One thing to notice here is that even in the parts of the image where I am observing, like his eye, it doesn't perfectly match, because what you're seeing here is G of Z star. You are not seeing, of course, I could take only the part that's missing and paste it here, and also do some smoothing and other extra tricks to use the information I have, but that's not my point here. My main point is this generator, if you use these tricks, actually produces this image that I think is very, very good reconstruction that fits the measurements. Also, interestingly, it actually made the mouth not smile symmetrically, perhaps because it didn't know what to assume here, or perhaps, and it also has some artifacts in some points here, but overall it's pretty good. So that's basically just to get you interested in the results, and then I'll talk about how we can do these kinds of things. Any questions?
Incidentally, I have a high resolution image if you want it. But
well, it's actually more interesting that this image that we get is 1,000 by 1,000. Okay, so we also made your image. We did super resolution for you here, right? So we started with this image that was very low res, and this image is 1,000 by 1,000. Now, it's not great, but you can still probably use it on your web page and avoid face recognition systems, right?
Could you comment a little bit more on the resolution mismatch? Because the generator was designed to generate images of a certain size. So what did you do? Did you just upsample this to the generator?
So super resolution is a part of this process. Yeah. So you can. Super resolution is one of the basic problems that we solve. So here is inpainting and super resolution. They all fit exactly the same framework. So you will see in a minute.
Okay.
Yeah, but yeah, it's super resolution is part of the problem, and we can handle it, no problem. All right. So let's talk about linear inverse problems. Everything is a linear inverse problem, like the previous, not everything, but this problem is a linear inverse problem. And when we have a linear inverse problem, we have a real image, that's X star. That's the real pixels of Vijay's photograph, all of them. But unfortunately, we don't get to look at all of them. We get to look at the matrix times X star. Now, if there was also super resolution, this matrix would perform the super resolution. So I will show how in a minute, but you can always think of there's some real image I'm looking for, and I'm observing it through a matrix. For example, in Inpainting, it will just literally just drop some coordinates. So the number of observations I have is M. The number of pixels I'm trying to reconstruct is N. And in this setting, this is known crucially. Otherwise, we have another family of interesting problems. And it's called the measurement matrix or the forward operator. This is the unknown signal I want to reconstruct, and these are the known measurements that I will use. Okay. Now, I'm observing, of course, y, which is smaller than n. So as you know from kindergarten, when you have 5 equations and 10 unknowns, that's not a solvable. That problem does not have a unique solution, right? So that problem has infinitely many X stars that explain the measurements. So it's an ill-posed problem. So you must make an assumption that X star has some structure. Otherwise, you have no hope of recovering X star. And the name of the game has been always, what is the right structure that we are assuming that A, models things correctly, and B, can be useful for reconstruction. Right? And the classical thing that people have studied in this beautiful theory of compressed sensing for many years is we assume that X star is sparse. So there are only K non-zero entries. The rest is assumed to be 0. And X star can be sparse in the standard basis, or it can be sparse in a known basis, and that's still fine for the theory. So we would like, in the simplest case, which is the noiseless case, to find the sparsest vector. This is the L0 norm that measures the number of non-zeros, the sparsest vector that explains the measurements. So this would be the ideal reconstruction algorithm for the noiseless compressed sensing problem. Unfortunately, this problem is provably NP-hard. So we have no hope of solving it. So instead, we relax it to this problem, where we replace this with the L1 norm of X, which is actually a linear program. And this you can solve algorithmically. And then you can hope that the solution of this is close or equal to the solution you would get from that. So this is called basis pursuit, by the way. And in the noisy case, it's called Lassa, and it's used very widely in all kinds of inverse problems. So people have studied for a very long time under what conditions on the measurement matrix A will it be true that the minimizer of this, which I can actually compute, is going to be equal or close to the minimizer of this, which I cannot. And I'm not going to spend a lot of time here, but there's a rich and beautiful theory started by Donoho, Candace, and Tao, and Romberg, Candace, and Tao, and also many, many other follow-ups that defines conditions on the measurement matrix A and says if the measurement matrix A is good, then X1, the solution of the linear program or Lasso, is going to be equal or close to the true unknown optimum. So this is the theory, and the theory tells you how many measurements you need. It needs you sample complexity. Assuming that the measurement matrix is created, let's say, randomly, then we have defined these things called RIP, restricted isometry property, or restricted eigenvalue condition. And we have theoretical results that say that if you make this matrix random with K log n over K measurements, where K is the sparsity, this is much smaller than n, right? Because K can be much, much, much smaller than n. Then with high probability, the measurement matrix will satisfy these RIP conditions. And then if it does, there's beautiful theorems that say that the convex relaxation is going to match the solution or be close to the solution of basis pursuit or Lasso. So this is the classical theory of sparsity and Lasso, which I also have worked on and have been inspired for a long time. But now I'm trying to take sparsity out of the picture, right? So this is what this talk is about. So sparsity is a decent model for natural images, but now we have these much better data-driven models, like deep generative models. And the central idea of this talk is let's replace sparsity with X is in the range of a generator. So that's what we're going to use. We're going to take sparsity out of linear inverse problems and model natural signals with generators instead. There's an interesting fact theoretically that says, actually, this is a proper generalization. So when I say X is in the range of a deep generator, that is a proper generalization of sparsity, because in this paper by Akshay Shushrut and Eric Price, they recently proved that you can create two-layer generators that have in the range only sparse vectors, okay? So basically, I can represent, if the desired structure is k-sparse vectors, we can model that with deep generators that have two layers and polynomial size. So the problem of assuming X is in the range of a deep generator is a strict generalization of sparsity, okay? Is that clear?
Cool.
Yes, yeah.
Okay, yep, okay, great. So the central problem that I was interested in is, okay, how do we solve problems assuming that X is in the range of a generator? All right. So like before, I have a vector, I observe linear projections, but now I have a generator that somebody gave me. Somebody spent a lot of money training a very complicated generator, and I know for now that the signal I'm trying to sense is in the range of this generator, and that this thing is much lower dimensional. So how are we going to recover X star given noisy linear measurements? And now I can ask you, wait, before we had sparsity, the simplicity measure, and that was the number of non-zeros of X star. Now the sparsity measure is going to correspond to the latent dimension, this thing here. And also another thing that will enter in this game is going to be the Lipschitz constant of this map, right? Because if this map is very non-Lipschitz, then this can be a very complex manifold. Whereas if this Lipschitz constant is small, it's going to be a much simpler manifold. Okay, so the complexity measures are going to be the latent dimension of the latent code and also the Lipschitz constant of the generator. So I'm replacing sparsity with a generative neural network. Before, to recover, we were using Lassa. What's the recovery algorithm now? So let's do it together so we can actually understand this problem. The simplest case is what I call inverting again. When I say inverting, I mean that I observe a full image, okay? So X1 is actually n-dimensional, in which case A is identity, right? So the forward operator is just identity, and I am just trying to find a Z so that the generated dream image of this generator looks as much as possible as my picture here. How could I solve this problem? That's the first question. So, and the answer is very simple. The same way you do anything in deep learning, you write down a loss function, which is, let's search over Z, the latent code, so that the generated image, G of Z, minus the pixels of my image, is as close as possible in the mean squared error. So this is, let's say, L2 norm. It's just the simplest loss function you can do. This is now a differentiable function in Z. So I can start with a random Z, get some random phase, and then start updating Z to minimize this loss. And this works pretty well. Okay, so it's not the best algorithm for inversion, but it's a very simple thing you can do. And you do gradient descent on Z, and you keep, of course, the weights here fixed. You're not messing with the weights. And this is what we got when we ran this on StyleGAN2.
Alex, there's a question by Lay.
Yes.
Hey,
oh,
Alex,
I don't see the question though.
Yeah, I just raised my hand. Yeah. So Alex, here we are trying to recover X or recover the GZ.
Very good. So these are very related, right? So if we assume that my picture is indeed in the range of the generator, there exists a magical GZ star which produces my face exactly. If that were the case, which means this generator is awesome, then searching for Z star is the same as trying to search for X1, right? Mm-hmm. Now, in reality, we don't hope that there is a Z star that produces exactly my face, but we are assuming, and I will show you that this is true empirically, that there is a Z star that produces a face that kind of looks like my face. So you can think of this as the manifold G of Z, and you can think that my face is maybe here, and we are trying to find a projection of the manifold as follows. And if this is a good generator, then we were going to get a pretty good reconstruction. Now, this particular person here, you can see he kind of looks like me, but makes me sad a little bit, a little older, not as much fun, right? So if you actually, so how you solve this optimization problem is actually non-trivial and key. So we have to do several tricks. We have to change the learning rate. We have to do adaptive. Actually, Adam helps a lot here, like an adaptive gradient descent as opposed to vanilla gradient descent. And we have to change the learning rates. So I think if you do more tricks in the optimization, you could get a better looking person, but you're never going to get, at least we have never seen actually getting a picture that looks like me. But we found another trick that I'll show you later. It's called this intermediate layer optimization that actually produces pictures that indeed look like me. So we have found a way to expand this manifold, and you will see that in the third part of the talk. But for now,
Alex, sorry. So I guess the advantage here is you get a generative model instead of just a single picture, right? So because if I just want to recover like your picture, isn't that have more efficient algorithm than just training a neural network for that?
So it depends what you mean recover my picture. If you observe my full picture, like this one here, if you're observing my picture, there's nothing really to recover. You have my picture and it's great. Now, but you can think of denoising. Let's say somebody went in and started adding random noise on my, now you may want to solve the projection problem because this will actually denoise it. You may also want to use this for compression because this Z that I found that produces this dude is actually only you know, I think 300 numbers, as opposed to the image, which is, you know, 1,000,000 numbers, right? So this is really a compression problem hidden in finding the right Z also, and also a denoising problem. Am I answering your question?
Yeah, yeah.
Okay, great.
Thank you. Yeah.
Alex, I have a question.
Yes.
So it seems to me that the quality of the result of this process depends on two things. One is the algorithm to find the Z for the given X, and the other is how good was your generative model. Exactly. And it seems to me in the sketch that you just drew there, you're just expanding the generative model, sort of to make it closer to X1.
Yeah.
Is this what you're doing?
So, okay, so what you said is exactly correct. There are two separate issues: the optimization, which is how do we invert a generator once somebody gives us a generator? And then there's a second, more complicated issue: how do we adaptively grow the generator to become a better generator? Hold that thought until the end of the talk, because I don't want to confuse these two issues. So for now, let's assume that somebody gave us a generator. It's here, it's sitting there. Specifically, this experiment is using style GAN 2. That's a generator. It's a pretty good generator, but it is not able to produce a better looking picture for me. But it could be that it can produce a better looking picture, and I'm just failing to find it because of the optimization. This is a non-convex optimization problem, and we have proven it's NP hard actually for 3 layers or more. I will show the result in a minute. So there is the optimization issues, but as you said, there's also the possibility that the generator is just not good enough and you need to buy a bigger generator. And we're going to talk about that later. But for now, imagine somebody gave you a generator and it's good, and we just want to solve this inversion problem. And
got it, thanks.
Very good. But yes, you are spot on identifying the two key issues. Okay, now the first problem was just inverting or denoising. But the first thing, by the way, we said this in our 2017 paper, and also independently from us, many other people proposed this because it's a super obvious thing to do. Another super obvious thing to do would be to train another neural network that takes X1 and produces Z. So this is called training an encoder. So people who like to train neural networks for everything, they will train an encoder to go from the pixels into the latent code. People who like optimization more like me will say, I'm not going to train a neural network. I'm going to actually do gradient descent in Z to find a dream that agrees with the measurements. Actually, both approaches can work better or worse depending on how much you tune them. I think of them as almost equivalent, but I prefer the optimization because it's principled. Now, this was just for inverting. But now, how do we solve inpainting? And that's what I want. That's what the first message I want to say. That if you can solve this problem, you can actually solve any linear inverse problem, and actually even non-linear, any inverse problem where the forward operator is differentiable. So let's understand that right now. Now I'm observing this image, which is this person with all these pixels missing. And I'm again emphasizing that these pixels are not black, they're actually missing, and I know they're missing, right? So I would like now to search for a Z so that G of Z, the generated image, agrees with these observations. But I'm not trying to find a person with a big black square in the center of the face, right? I'm trying to find a person so that it agrees on only the observed pixels, and in the unobserved pixels, I'm leaving the optimization unconstrained. So the way I'm doing that is I'm making the process of removing pixels a matrix. It's very easy to see that dropping pixels is just a submatrix of the identity, and this is what I am observing. And I am defining my loss now to be, I want the measurements of the generated image to agree with the observed pixels. And again, I do gradient descent exactly like before, starting with a random Z, and I get this image. Now this is using DC GAN, so it doesn't look as high resolution, but it's pretty good. Now, or it was pretty good in 2017. Now we have better generators. I want to emphasize that the mouth, for example, does not actually match the real mouth, because this generator is not able to perfectly produce this mouth, but it's able to do reasonably close, right? And as we said, if we believe that our generator is not good enough, we need to replace it with a bigger one that has a bigger latent dimension. So, yes? Okay, so that's how you can solve inpainting. How can you solve super resolution? Another question that was raised earlier. Well, super resolution, you can think of, if you know the forward operator, the blurring operator, that this pixel you are observing is a convolution of the original high resolution image convolved with a blurring kernel that I'm assuming here for simplicity that it is a known matrix. So I can write this as A times X star, where A is this matrix that convolves the clean pixels with the blurring operator. Again, that's just a linear inverse problem. I can write, actually, it's the same loss function. It's just the matrix is just now blurring as opposed to dropping pixels. And I do gradient descent again, and I get this super resolution image. And you can see how I can combine super resolution with Inpainting to, as long as I know the measurement matrix, I can solve any problem and find any z so that AG of z agrees with the measurements. So this is the algorithm, okay? Do gradient descent in z space to satisfy any measurements you have. And the magic is that you actually obtain useful gradients in z because you are back propagating through the measurement process and the generator all the way back to the latent code, okay? So this is the algorithm we proposed in this paper that we call the CSGM, the compressed sensing with generative models. And you can also quickly realize that you don't actually need A to be a matrix. It can be any differentiable operator, right? It can even be a neural network. So as long as this is a differentiable machine, I can just update my Z to match the measurements, and you can do phase retrieval or all kinds of nonlinear inverse problems too. So this is how you solve inverse problems using generators in general. This is the algorithm we proposed. Is that making sense?
Yes. So actually, a quick related question. Mm-hmm. So if you're doing these kind of inverse problems, couldn't you use it for decoding algorithms?
Decoding what?
Decoding algorithms for, I don't know, communications and stuff.
Yeah, so we are working on using it for compressing channels. So if you have a wireless channel in a very with a very large number of antennas, then you can think of making a generator for the H matrices. And now if you have a generator for the H matrices, you can solve a compressed sensing inverse problem for channel sensing and channel estimation. The challenge, the difficulty is to make a generator for the things you are trying to model. So for example, with one group, we're working on doing this for MRI, but we need a generator for MRI images. And then if you want to do it for wireless channels, you need a generator for wireless channels. So if you have such a machine and it's differentiable, then you can use it like this to solve any inverse problem with a differentiable forward operator.
Thank you.
Okay? Great. Okay. So as I said, there are other methods of solving inverse problems that, for example, supervised end-to-end inversion that I'm not going to talk about now, but if people are interested, we can talk offline. And we have written a survey which tries to make a taxonomy of different types of solutions. Okay, so I'm going to compare it briefly to Lassa, which is a sparsity-based technique. And I want to show you that here we're observing only 500 measurements, random Gaussian, while the dimension of the vector is 13,000. So these are the reconstructions we get. And these are the reconstructions that Lassa gets, assuming sparsity in the DCT domain and in the wavelet domain. And we do better because we have a stronger prior, right? We have a data-driven prior that knows faces, whereas here, the only thing that Lassa is using is that an image is sparse in the wavelet domain or sparse in the DCT domain. I want to show this plot that has an important point. I'm showing here the performance of our algorithm using DC GAN and DC GAN with an extra regularization that doesn't make a big difference. So look at this performance. Here we have measurements. So we're making random projections and we're trying to reconstruct an image. And here I'm showing a mean squared error. And I'm comparing, this is the GAN methods, and I'm comparing them to sparsity-based methods. And then you can see that the gap here can be up to 10x in measurements, or 5x, depending on which point, which regime you are. But there's another important point I want to say, that after a while, after maybe 600 measurements, the performance of the inversion we get with the generator is no longer improving. And actually sparsity-based methods in this regime are actually outperforming the generative priors. And there's a simple reason for that, that once you get in this regime of high measurements, you have now reached the representation capability of your generator. It's what Achilleas said, that if you are in this regime, the latent dimension of your generator is not big enough, and you're projecting the best possible dream the generator can produce, more measurements are not going to help you anymore. And then you just need to get a bigger generator that can benefit from the more measurements. Whereas sparsity is able to benefit from more measurements because it's a very flexible generator if you relax the sparsity amount. Okay? Very good. So I'll move on and I'll take questions at the end because I'm kind of running low on time. I assume I have like 8 minutes or so? Is that good?
Yeah, roughly 8 to 10 minutes. Yeah.
Okay. Okay. So I want to say that all this stuff I have been saying is not new. It's not that we invented it. Many people have been talking about structure beyond sparsity, going back to early work by Rich Baranyuk's group, Volkan's group, and many other groups. Marco Duarte and Yorina Eldar and many others have been talking about projections on manifolds from at least 2009. The difference of all these works to what we are doing is really the fact that we're using differentiable generators and backpropagation in our inversion, right? So this is really the difference, because people have thought about learning the manifold of signals forever. It's a very natural thing. But the specific way of doing it using a GAN and then backpropagating through the generator to update the measurements is what we are proposing here, and that is different. But of course, we are inspired by all these classical works. Now, I want to tell you a little bit about the theory of what we can prove for this problem. So this is the full layout of the talk, and you can see regretfully that I've only made it this far, and I wanted to talk about this thing and this thing too. So that's why I'm gonna rush a little bit. And then I can take questions at the end. So the CSGM is the compressed sensing with generative models setup, and we can prove some guarantees about it by generalizing this theory for RIP. That's basically inspired by compressed sensing for sparsity. So this is our main result, that if you make a random Gaussian measurement matrix with the number of measurements being k d log n, and now k is the latent dimension of the generator, d is the depth of the generator, and n is the ambient dimension of the pixels you're reconstructing, then the reconstruction is going to be close to optimal. So we get, this is the type of result we get. The reconstruction that we get is z hat. And we say the generated image that you get by solving this optimization problem, which is the algorithm I proposed, is going to be constant factor from this. And what is this? This is the best image the generator can produce, right? So relating to Achilleas's comment, if this is big, then your generator is broken. You need to buy a bigger generator, right? But I'm telling you that if you have this many measurements and you minimize this, you are going to get an error that is close to the optimal error the generator can produce. And the important thing is that this formula doesn't have the measurement matrix here, right? So you're minimizing with the measurement matrix, but there's no A in this error expression. And that's the whole point, that if you have enough measurements, the measurement matrix is not creating a problem for you. You're getting an approximation in the pixel space, right? And we have a more general result, also in this 2017 paper, that if you don't have, by the way, this result is only for matrix multiplications and ReLU activation neural nets. And this result is in general for any generator that is Lipschitz. And we need k, the latent dimension, and L being the Lipschitz constant of the generator here to be in the measurements. So assuming here that the generator is an L Lipschitz function, which is always true for real generators. So the way we prove these results is we basically build on this idea of RIP. RIP is a property for a measurement matrix that says that all the sparse vectors are far from the null space of your measurements. Because if there's a sparse, this is in classical compressed sensing. If there's a sparse vector in the null space, you are going to be blind to it. You're going to confuse it with zero. But so similarly, for generated vectors, we define a set restricted eigenvalue condition that we call SREC, that asks that the differences of pairs of generated images is far from the null space. So this is the key condition we define. And then we have two lemmas. One says a random matrix with this many measurements will satisfy SREC with high probability. And the second lemma says that if a matrix satisfies SREC, and you could solve this optimization problem, which is non-convex, by the way, and probably NP-hard in general, as we have shown. If you could still solve it, then you're going to get a good reconstruction in terms of the best reconstruction that your generator can afford. Okay, so this is kind of the theory that that we have established, and there's many open problems. For example, different statistics for measurement matrices, and so on. So I'm going to skip this because I'm running out of time, and I just want to briefly talk about intermediate layer optimization in the 5 minutes I have left, and then we can discuss or take questions. So, what is the problem? So I'm skipping some stuff here, and I am getting here. What is intermediate layer optimization? So this is hot off the press that, as I said, will appear in Nurip's workshop. Intermediate layer optimization says the following thing. Instead of, so I have a generator that takes Z, has a layer G1, produces H1 here, and then passes this to another generator, G2. So the final output is the composition of G1 of Z and G2 of G1 of Z. Compressed sensing for generative models said search over this vector so that the dreamed image agrees with the measurements. And in my case, this was my image, and this was the dreamed image, which is kind of sad. As I said, it kind of looks like me, but I'm not very happy with it. So then we said, all right, after we get this, let's throw away this part of the network completely, and let's optimize over this H1. So this is step 2. Step 2, minimize over H1 to get to, and using only this part of the generator, right? So this part is now thrown away in the trash. But we initialize from G2 we initialize with, sorry, this is G1 of Z star. I messed up this. This is G1 of Z star, which is the point where it was producing the previous phase. Now, if you look at this phase, it looks perfectly identical to mine, but it's actually a generated image. Okay, so I'm putting it here as a big image, and it looks near perfect to me. There are some artifacts you may notice in the eyes and so on, but it's basically a near perfect generated image. So I'm thinking of putting this image on my webpage instead, you know, to avoid maybe automatic face recognition systems and other things. I don't know if it is robust to those, but that's another interesting thing to think about. So last thing to say, and I wrap up. If you take my image and you just do inpainting with this intermediate layer optimization idea, where you move to the next layer, you get this image, which is an interesting guy, looks like me, but I mean, the network has no hope of knowing how my eyes look like, right? So that's a fair inpainting. But then if we amplify the perceptual distance more compared to the mean squared error, there's 2 hyperparameters we are controlling, and we go in intermediate layer optimization in deeper layers, we are expanding the manifold so much that we're leaving natural images, right? We're producing some weird looking extensions of humans now. So when we did that just for fun, we optimized over, so we have a different loss, mean squared error plus 2.5 LPIPs, and we got this cartoonified reconstruction of me that I found entertaining. And then when we went even deeper and we also increased the LPIPs hyperparameter even more, we got an even more absurd completion. So as we are traveling in the space of the generator, we are expanding basically what images can be produced, leaving natural images and getting more into, you know, Picasso and stuff like that, which is kind of fun. So in conclusion, modeling high dimensional distributions has been key, obviously. As I said, sparsity has been successful and conditional independence has been successful. And now we're trying to use deep generative models to do the same things for channel coding and source coding and many other problems. Now, all the training and inference tasks in deep generators use gradient descent. That's the key difference. And also, all are poorly understood theoretically. So there's numerous open problems. But the main message, if you're going to take a message from this talk, is every time you have a paper that says something is sparse, replace that with X's in the range of a pre-trained deep generative model, which actually, as I said, is a proper generalization. Now you have a new project that you can work on. And if you have a good generator, it will actually also work better empirically. There's all kinds of interesting problems like bias that we can talk about. Like in this super resolution problem, There's this famous on Twitter example where this was a low sampled Obama and the generator made him a white guy. And people have been talking about fairness in inverse problems using generators, which is another interesting problem that I'm working on. But you can see that the super resolution is incredible, right? It starts from this input and it produces images like this. But it does have biases that are interesting to study and see how you can mitigate them. So conclusions, we need provable algorithms for inversion of generators. Already that's a very interesting optimization problem. How do we fit generators to data, of course, is a big open problem. We seem to be doing well with images, but not so much with other data sets. Evaluating if a generator actually fits well is another interesting problem. And imposing physical constraints on the generated data is also a very interesting problem for all kinds of inverse problems where we know they have to respect a differential equation or some other physical constraint. So I think that's another very interesting problem that I'm working on and I think other people are working on. We had a recent paper where we have errors in the measurements. This is the link for that. This has also been studied in the context of sparse recovery, and the techniques nicely connect to the techniques for robustness in sparse recovery. So it's pretty rich theory and many more things to do in robustness. And also, as I said, correcting bias in the learned prior. Furthermore, getting conditional sampling, marginalization, and many other changes are all open problems for deep generative models. And if you're interested, I have links to my Twitter account. Also, we have papers. We always post our papers and our code. And I would love to follow up more if anyone has any questions on anything that I spoke about. Thank you very much.
Well, Alex, thanks. So let's do one thing. Let's go through the discussions and then see if anyone has any questions. So in terms of priority order, I think I'll go with Cameron first, and then Jeff, you can follow after that. Is that okay?
It's fine, except I have the slides that I.
All right, that's fine.
Yeah, the slides are first, so I mean.
Oh, you got them up? Okay, go ahead, Cameron. You go ahead then.
I know. I
Oh, okay. I'll go ahead because we had planned the other order. We kind of had a plan, if you don't mind. Are you?
All right, that's fine. You can follow that. Yeah,
what are you seeing now? Are you seeing the slides?
Yeah, you can move it into the presenter view. I think
I think I stopped sharing, right?
Yeah, you did. Yeah.
Okay, great. Okay, so now you can share. Yeah.
Does it look right now?
Yeah, I can see it.
Yeah.
Okay, so it's, first of all, thank you for that delightful seminar, and it's really a pleasure for me to actually sort of meet you in this virtual way, because for the last several years when I've been giving overview talks about machine learning based methods for image reconstruction, your work is with Ashish Bora is one of the first things I mention, and I show the cost function that you showed today, where you do a reconstruction based on the output of this generator. And I point out the challenge of the non-convex minimization that you've alluded to, but I also point out the potential risk of having a reconstruction that's in the range of generators. So you need, as you called it, an awesome generator, I think, to at least in the medical imaging setting, to want to use this. And so I've thrown out, but we have not investigated the possibility of a variation on this, which instead of asking for the output to be in the range of the generator, I asked it to be close to the range of the generator. So think of the generator more as a regularizer than just as strictly speaking, a generator, right? So this is a little, in dictionary setting, this is a little more of a synthesis model. This is, it's not quite analysis, but it's a little bit more like that. I was curious if you've looked at that at all, whether you think your theory would generalize to that formulation, whether you think it's a bad idea. What are your thoughts about it?
I think it's a very natural idea, and I think it fits very nicely. Yeah, basically we've been doing this, of course, just to simplify things, and also when we try to prove something, we work with the simplest case. But you're absolutely correct. At the end of the day, the right thing to say is you want to explain the measurements on one hand and produce a realistic image on the other. And by the way, I'll make a side remark. The way when I started this, I had a different idea. I had the discriminator of a GAN. So I don't know if you know the discriminator. The job of a discriminator is to take pixels and tell you if it's a real image or not, right? So the first thing I told my student to do is exactly what you wrote there, but R was literally the discriminator of the GAN. Mm-hmm. And that failed miserably. And then what we realized is that if you take the discriminator of a GAN and you feed in pure random pixels, independent random noise, it will tell you that it is a real image. And then we realized that the discriminators are not really doing what we think they're doing. They're not realizing if an image is a real image or a fake image. They're realizing if an image is generated by the generator they grew up with or not.
Right.
So it's a much more narrow, but absolutely, I think what you say is indeed exactly correct. And if I had an R of X that makes real images, gives me big numbers for real images, that's the right way to do it. And you're right. Everything you say is perfectly, of course, the right way to think about it. It's just a little more general than the way that I wrote it. Yes.
So Cameron was smiling when he talked about that because he's actually been working on the discriminator approach with.
I did try that approach and it did fail.
And this is the problem with the positive results publication bias in our field, right? It would have been useful if you had told us that that wasn't going to work before we went down that path. So
yeah. I try to talk about my failures, but I don't write about them as much.
So in fact, these slides are a couple of years old. And don't worry, VG, I only got 68 slides.
That's fine.
There's these are results a couple of years ago from one of Google's generators, and there's these little blemishes or whatever, and it might be fine for video games and making fake Twitter feeds, but it's concerning to me for medical imaging, which is why I think something that's a little more robust imperfections in the generator. Oh, and I'll skip this. I have some examples from another student's work of like neural networks completely obliterating tumors, even though they were trained with lots of tumors. I think at this point, I'll hand it over to Cameron.
Yeah, so thank you for the talk. It's amazing work. I've definitely looked at this and run it on some of my own problems. And I've had fun trying to optimize these generators. Like here's a graph of one of the problems I worked on where I had, I tried with 10 different random initializations, and we picked the one with the smallest error, as I believe it was described. And I really like in your paper, it's just optimize with gradient descent. There's other papers that kind of describe other ways to optimize it using like a projected gradient descent type method, or like this paper that was by Sean Hedge, where they talked about doing like a second step where they do a projection. And I guess there's been a lot of papers on like how do we invert these GANs, and I'm curious on if you have like any, I guess, general best practices or techniques that you found that have helped you in optimizing and finding the inverse of these GANs. I know you've worked on more.
Yeah. So the best trick I recommend is to have very, very good students who are very, very, very persistent. And honestly, yeah, we have seen difficulties in optimization. We do random restarts. We saw also the Pulse paper by Duke that was doing that had also several interesting tricks into how it was adjusting a little bit the statistics. Honestly, I have two recommendations. The first one is it really depends on the generator you have, like so we spend a lot of time with DC-GAN, which was good for 2017, but since we've been using recently either invertible generators, which is another can of worms we can talk about, or StyleGAN 2. So what I am most excited right now is StyleGAN 2 with this intermediate layer optimization. So if you do that, I mean, that's the results that I showed in this talk. We're using that, and it's just beautiful. And even when it fails, it just produces really interesting images in all kinds of ways. So I don't know what generator you used, but it's very sensitive to that for sure. Also, did you do cyclic learning rate variations or fixed learning rate?
I believe it was a fixed learning rate, probably.
Yeah, so learning rate also was an issue for us. Random restarts you mentioned. There's a lot of bells and whistles. That's why I'm also a big advocate of sharing code. And a big part of our discipline in terms of the empirical results is our code, right? And so of course I like theorems. I'm a theorist at heart, and I want to prove bounds for random random measurement matrices, and that's a big part of what I like. But also in the empirical side, by the way, please do contact us, and we'll be very glad to share code with you and work with if you're trying to replicate any one of our papers or you have any issues with. We really believe in collaboration and communication because we have suffered through the same things. Yeah. So
Yeah, it sounds like it.
Yeah.
So you mentioned like the style GAN and some other GANs that you've been using. In general, like I guess when I look at the outputs of these different GANs, like some of them, like this one looks like it produces really good output and this one looks like it produces really good output. How do you, in general, choose a GAN? Is there like architectural choices? Do you want as small of a latent size as possible with as good of a quality, or does having a larger dimension make it easier to optimize?
Yeah, so I don't know. So by the way, sorry, I forgot one more thing. For DC GAN, actually also for style GAN too, but even more for DC GAN, one thing we found that's extremely sensitive is any miscalibration in the cropping. So if you move the image, if the image is not correctly centered or aligned, as you probably have found out yourself, it's going to fail miserably again. It's very sensitive to this issue of positioning correctly. So we spend a lot of time placing the images exactly. So the eyes have to be exactly in the center and so on. And if they're not, you have to build some pre-processing tools that align and only then rely on DC GAN. Style GAN 2 is sensitive to that too. If you use ILO, it's much more able to produce all kinds of other wacky images that are not centered. But you pay because you're leaving the manifold of natural faces and you can get Picasso type of things. So I think there is a trade-off there, and I would love more input from how to do the optimization in a more principled way. But honestly, we are a little bit in the woods. We are basically trying heuristics. Adam helps. I think you used Adam too, you said, right?
Yeah, I used Adam, yeah. Yeah,
so we use Adam, we use cyclic lights. We have to correctly place the image, crop it correctly. And random restarts are basically some of the tricks we helped us. But style GAN 2 has been the biggest change for the quality of the reconstructions for human faces. Now, if you're trying to train a generator for MRI or another medical imaging application, I would love that. And that's the kind of thing we need to have a real impact in another domain is somebody training a very good generator. And I think this will happen because these things are making progress. They're making impressive progress. Like from DC GAN to style GAN 2, it's already a shocking improvement in 3 years. So I think it will happen, but we have to do it. Somebody has to do it.
Yeah, thank you. It takes a long time just to get those like skills of like what are the things that work, and I appreciate your experience. I guess like kind of on that point of like with medical images, sometimes if there's like a piece of metal in the body, we don't know necessarily like the range that the scale of the output image. And with generally with like a dictionary model, we could just scale the sparse codes and the output also scales with that. I guess in a generative model, we can't just scale Z to get a larger range from the output as far as the values that the image takes on. Is there a way to like robustly handle like if you don't know the scale of your measurements, how?
I haven't thought about this problem, but it sounds like a very interesting aspect that I haven't thought about. You're right. If I multiply Z by 2, G of Z doesn't get multiplied by 2, and you could search for some other Z that produces 2 times G of Z1, I guess. But no, I haven't thought about it more than that. But it sounds like a very interesting problem, actually.
I guess kind of close to what you said before. You generally do a lot of pre-processing on your measurements to kind of get them to the point where they'll be in the same range of the generator.
No, for images, no. For pixels, for faces. You were asking me in my experiments?
Yes. Yeah.
Not so much. I mean, the experiments we show are all human faces that I get from the web for people I want to harass, like VGA and stuff. So I just basically we do crop them, and we do make sure that they're leveled and they have to take the full dynamic range.
That's what
pixels and basic things like that. But we don't. It wasn't very sensitive to that. The cropping and the alignment was the biggest issue that we found.
But you're normalizing to be 0 to 255 or 0 to 1 or something like that, right?
Yeah, there is. I think in the code there is. So the cropping and stuff we do manually in image processing, but the renormalizing, I think we do that. Yes.
So the grayscale scale is one thing that varies in medical imaging. Also, the number of pixels varies, right? In MRI, there's thousands of different protocols, each producing images with different sizes. So
Yeah.
But my impression is these generators are designed for a given output size, right? Are people working on, you or others working on generalizations that would be a little more universal? I mean, because after all, faces are in an analog world, right? There's some sampling, but there really lives in a manifold in a continuous space that we then sample.
Yeah.
Is anybody working on that?
You know, I worked on a related problem where I was trying to make generators for ImageNet.
Okay.
And for ImageNet, it's much, faces are so, especially when they're aligned, like these data sets we have, they're actually an easier data set than it looks. We are very sensitive to human faces, but they're very aligned and they don't vary that much. But when we were going, you know, we had like landscapes and dogs and cats that can be different parts of the image. So we did face some of those problems, and it was much harder to train good generators for ImageNet. Yeah. Now, if you have even changing resolutions, I haven't worked on that problem. I think it will be very difficult. And honestly, my approach would be to circumvent that and just make everything in the same resolution and pick some cropping and just circumvent this issue, because I don't think that we shouldn't be asking deep learning to do that for us, because I think we're better off solving this separately somehow, I think.
And then my last question is, you start out with this beautiful overview of sort of learning distributions, right? And then, but the distributional aspect kind of disappeared, or was not emphasized, let's say, throughout the talk after that, right? That there is this variant that I think we have even on our slide here, where you have this penalty, which you could say is sort of getting the Gaussian distribution. But other than that, it kind of doesn't appear. And then I really wondered, once you have this intermediate layer optimization, is there still a distributional aspect to that? I do think I'm curious what your thoughts are. Is that important to have sort of a statistical model as opposed to just a generative model that you feed in parameters? What do you think about that?
I like your question. I have been split about it. Okay. So I'll tell you what my current thoughts are, but my short answer is I don't know. We also added, you know, the L2 norm of Z and things like that. And we were also thinking about diversity in the generated sample. So you don't just want to reconstruct one image, but you want to reconstruct many times. And then you want to, it's useful, for example, for uncertainty quantification. Because
exactly. That's where I'm coming from. Yeah. Mm-hmm.
So we have a paper on that. I actually found out another interesting aspect of this issue. You can think of the CSGM framework as doing maximum likelihood, essentially. Sure. If Z was Gaussian and so on. But what we're finding is that the right thing to do, and we have a workshop paper on that, I'll be glad to share it with you. It's in the deep inverse workshop. We find that in many situations, you really should not be doing maximum likelihood, but rather you should be sampling from the conditional.
Okay.
Because the maximum likelihood, you know, will pick the spot. If your density has some spike somewhere that's very tall, but doesn't contain a lot of mass, maximum likelihood will prefer to pick that, even though it's really the wrong. So we can construct cases where maximum likelihood can be a terrible idea. One example is also in the issue of diversity of reconstructions, right? So when they get these white Obama reconstructions, you can think of the generator saying, okay, I'm observing this image, I have to produce a single reconstruction. And I have a prior that, I don't know, 13% of Americans are African American or something. So if you force me to produce a single image, it may not be, it's a very different thing than forcing me to sample from the conditional. Right. So I actually believe, and we have some theoretical results on that also, under several assumptions, of course, that sampling from the conditional, so one way to sample from the conditional easily extending the CSGM framework is with Langevin dynamics, which basically means just add noise to the gradient descent. As you're doing this gradient descent, just pepper it with noise a little bit and you're going to get in every iteration, right? And there's a right amount of noise. The scale of the noise is given by Langevin dynamics, but you can see how it's also it also comes from some discrete version of a differential equation that I don't pretend to understand. But I just think of it as CSGM with random noise in the gradients. and it does produce diverse samples. And under some conditions, I said we can also prove that it is actually a better way to reconstruct than maximum likelihood.
So Jeff and Cameron, thanks. I think there is a question. I wanted to ask if anyone else had questions. So just, so I think Clay raised his hand. So Clay, go ahead. If it's a short question, because I'm going to go with some others if they want questions.
All right. Just a comment on the one advantage of having the generative model. It seems like it would make it easier to do adaptive sampling, where you're selecting one row of your sensing matrix at a time to, maximize the decrease in uncertainty in some sense.
I see. You say that I can select which I pay $1 for a measurement. I'm picking which measurements I query.
Right.
I see.
Right.
I see. Yeah, I haven't thought about that, but that's a very natural problem actually. Has anyone done that for compressed sense?
Well, I mean, they've done it in MRI, right, to design your trajectory in K-space, right?
Yep.
I don't know.
Not with generative models, to my knowledge, but with sparsity models.
Right. It's been a theme in compressed sensing for sure.
Yeah, you're right. It's a very interesting problem, and I haven't thought about it. I guess we could quantify the value of a measurement. Yeah.
So I had just a simple question, which is, how would one go about generating or learning a generator for medical images, since you don't have the training images in the first place? Like with faces, you have real world training images.
Yeah. So I'm not really very good at answering this because I don't know anything about medical imaging. But I think that people are trying to combine these deep image prior type of techniques with pre-trained generators, and I think they do have a lot of scanned images, right? Isn't there like big databases of MRI images?
For some kinds of scans, right? So there's some where we have plenty of training data, and there's other situations where we don't. So, so the low-hanging fruit at the moment is to work on the cases where there's lots of training data. Although lots is maybe still not enough for learning a GAN. That's
actually on that point, there was a recent development. And by the way, one of the things that's the most fun of working in this space is that everything changes every 6 months. So I mean, there's so much rapid development. So StyleGAN 2, there was a paper that was doing data augmentation, and they were able to train StyleGAN 2 with, I believe, only 2,000 or 5,000 images, as opposed to 100,000.
Wow.
So, and this is for 1,000 by 1,000 resolution, and so we were able to actually get StyleGAN 2 to produce dogs and cats with otherwise for Celebay or Flickr, we have much bigger data sets in the hundreds of thousands. But I think right now we can train StyleGAN 2 on 1,000 by 1,000 resolution with in the order of, I believe, 5,000 faces or dogs. So we may be getting to the point where I don't know how many images these databases of scans have, but we may be getting to a much more manageable domain. And they do data augmentation techniques. Every image in the training set, they do all kinds of little rotations, I think, recroppings and kinds of tricks to produce essentially virtual samples from a single sample.
Cool.
But I haven't read it, but I was very, very happy with that paper because I was also overwhelmed with the difficulties of training a generator on any other domain.
Great. So Alex, thanks again for a fantastic talk. By the questions and everything, and the fact that you put my face up and mangled it, I think it went very well.
Thank you.
And yes, thanks again. All right. This talk will be up soon, so if you want to mangle it further, you're all welcome to do so.
Okay. Very good. Thanks.
Thanks. Bye.